Calculating the equilibrium constant. We've learned how to write an equilibrium constant expression from a chemical equation. So how do we find out what the number for the equilibrium constant is? The most direct way is to measure the concentrations of the reactants and the products at equilibrium and plug them into that equilibrium constant expression. So here we have a simple reaction, and we're given molarities of each of the reactants and products at equilibrium. A temperature is specified because the equilibrium constant will be different at different temperatures, but again, that doesn't come into the calculation. So the first thing we have to do is write the expression. So Kc is equal to the concentration of the product, Hi, and that has a coefficient of 2, so it has an exponent of 2, divided by the concentration of the reactants. They have coefficients of 1, and so they have exponents of 1. Yeah?
If the reaction is flipped, so it's like 2Hi, H2 plus I2, would that switch?
Yeah, so if this reaction, if the equation is written backwards, you would write the equilibrium constant expression backwards. It ends up being inverted, is what happens. That's the 1 over. Yep, exactly. So then we put our numbers in here. The concentrations always are in molarity, moles per liter. We don't put the units into the equation because technically it's a ratio of this to 1 molar, and so it's unitless, and K ends up being unitless. So we don't have to worry about the units. So 0.78, and that's going to be squared, divided by the concentration of H2 and the concentration of I2. So we got 0.78 squared divided by 0.11 divided by 0.11 equals, and so we get a value of, calculator gives us all sorts of digits, 50.28, and it goes on and on and on. So we would round that to 50 with a decimal point, or 5.0 times 10 to the 1. And there's no units. Any questions? So this is the same reaction. Here's a table showing initial concentrations of these different reactants and products, the equilibrium concentrations, taking those equilibrium concentrations and plugging them into the expression for the equilibrium constant. And we find that we can vary the starting a lot, and these numbers can look very different, and yet it always gives us the same equilibrium constant because it is a constant. Yeah.
So what role do those initial concentrations play?
What role do the initial concentrations play? Well, I guess you could look at this and say, well, it doesn't actually matter what the initial concentrations were. It will come to the same type of equilibrium. The equilibrium constant will always be the same. Some of these we have equal concentrations of the reactants because we started with equal concentrations. But if we started with different concentrations of the reactants, then when it comes to equilibrium, they're not necessarily going to be the same as each other. Yeah?
Can the equilibrium concentrations be more than the initial concentrations, or that's impossible?
Well, you can't create atoms, right? And so like in this one where we're starting just with the reactants, the only thing that can happen here is that these can react to form the product. You can't get an equilibrium concentration of I2 that's higher than what you started with because there was no product to react and form it. Other times, though, here this started with 0 I2, and we end up with 0.055 molar because that was interesting. The product reacts, the reverse reaction occurs because there is no H2 or I2. And so the reverse reaction occurs, and then we do have some. So the equilibrium constant is the same regardless of the initial concentrations. The equilibrium concentrations are not always the same, but they have the same relationship to each other. And that relationship is described by the equilibrium constant expression. Any questions? So we can also calculate the equilibrium constant if we know the initial concentrations and the equilibrium concentration of one of the species. Could be a reactant or a product. We can deduce the equilibrium concentrations from the stoichiometry. So here's an example. We have A reacting to form 2B. So I would like to formally introduce you to an ice table, okay? You're probably going to have a love-hate relationship with these. We're going to use a lot of them. It helps us to organize and figure out what's going on in equilibrium situations. So here we have the reactant and the product. So there's columns for each reactant and each product. And then there are going to be 3 rows: initial, change, and equilibrium. And it's called an ice table because initial, change, equilibrium spells ice. So in this example, we've got initial concentration 1 molar for A and 0 of B. We don't know what the constant is, but the concentration of that reactant was measured at equilibrium, and we know that it's 0.75 molar. We can figure out what the other concentration is. So what we do is we look at this and we say, okay, well, we started with 1, a change occurred, and we ended up with 0.75. So how did it change to get from 1 to 0.75? You lost 0.25, right? So the change here for the concentration of A is negative 0.25. From that, we can figure out what the change is for B. You're going to make 2 atoms of B for every, I guess they must be molecules, 2 molecules of B for every 1 molecule of A that reacts. So if A decreases by 0.25, then B must increase by 2 times 0.25 because of the stoichiometry. See that? So this is plus 2 times 0.25. So 2 times 0.25 is 0.5, and you add that to the initial concentration, and you come up with 0.5. Now I know the equilibrium concentrations of everything in the reaction, and I can calculate the equilibrium constant. Because the expression is Kc equals the concentration of B squared divided by the concentration of A. And then I plug the numbers in. Concentration of B is 0.50, I'm going to square that, divided by the equilibrium concentration of A, 0.75. So 0.5 squared divided by 0.75. 0.33. Any questions? Make sure that you understand what I did here. Otherwise, the rest of it's not going to make any sense. So let's do an example with an actual chemical equation. So the reaction shown between carbon monoxide and hydrogen is carried out with initial concentrations of carbon monoxide at 0.27 molar and hydrogen at 0.49 molar. At equilibrium, the methanol concentration is 0.11 molar. Find the equilibrium constant. So we need to make an ice table. So we can actually just build the ice table below the chemical equation. So here's I, initial, C for change, and E for equilibrium. We're given initial concentrations. So carbon monoxide is 0.27. And hydrogen is 0.49. It doesn't say anything about the initial concentration for the methanol. What should we assume that it is? 0. Normally, when you do a reaction, you put the reactants in there, and you don't start out with any product. So this is going to be 0. We're given an equilibrium concentration for the methanol is 0.11. So now we have to figure out what's happening. Well, we're going to look at the methanol because that's the one that we know the ending for, the equilibrium concentration. So it started at 0, it ends up at 0.11. So this must have a change of 0.11. Okay with that? Well, if this one went up by 0.11, what happened to the carbon monoxide? It goes down by 0.11 because these have the same coefficient. One of these makes one of those. If I made one of the methanol, I must have used up one of the carbon monoxide. So this is going to be negative 0.11. What's the change for the hydrogen? It's going to be 2 times negative 0.11. Because it requires 2 molecules of hydrogen for every molecule of methanol that's made. Any questions? Now you add those columns. So 0.27 minus 0.11 is 0.16. And 0.49 minus 0.22 should be 0.27. Correct me if I screw up. Then we need the equilibrium constant expression. So Kc equals the methanol divided by carbon monoxide and hydrogen squared. So I'm going to have 0.11 over 0.16 and 0.27 squared. I'm getting 9.4. Any questions? Mm-hmm.
So can the ice table only be used to find new concentrations at equilibrium, or?
The ice table can be used to find a lot of things. Yeah.
I have a question. So C for negative, how can you tell like if it's a negative 2 or a positive 2?
Oh, that's a good question. So how do we know if this is a negative change or a positive change? In this reaction, we only had reactants, and so the only thing that can happen is that the forward reaction would occur. So if the forward reaction occurs, the reactants go down, the products go up. Sometimes you're not going to be able to tell which direction, or it may go in the reverse. So if you started out with products and no reactants, then the reverse reaction would happen, and the change for the products would be negative, and for the reactants would be positive. So the change can be positive or negative.
Does it matter if the negative is in front of the 2 for the change, or if it's within the?
No, it doesn't. You could write this as 2 times negative 0.11. That would also be fine. Yeah.
So you do this process even with liquids and solids, or we're going to get to that?
Well, with the liquids and the solids, their concentrations don't change. And so in the equilibrium expression, they're not going to show up.
So it's the same thing like in chapter 14, we would just exclude them?
Well, that was actually in chapter 15 where we exclude them. Yeah, the previous section. Yeah. So if it's a gas or a liquid, we're going to exclude it.
Solid or liquid?
Sorry. Liquid or solid. Any other questions on this one? Let's do another example. Reaction shown is carried out with initial concentration of methane of 0.087. At equilibrium, the hydrogen concentration is 0.012 molar. Find the equilibrium constant. So again, ice table. So initial concentration of the reactant, 0.087. When it doesn't specify the others, you just assume that they're 0. We're given an equilibrium concentration for the H2, 0.012. So the change for the hydrogen is that it went up 0.012. What would the change for C2H2 be? 0.004. So this goes up at 3 times the rate that this goes up. So this change is 3 times larger than that one. Does that make sense? You could think of that as this is equal to 3 times plus 0.004. So this would be the increment, and this went up 3 times that. So then this one is going to go up by 1 times this. So this one's going to increase by 0.004.
So you're always basing the change off the lowest coefficient?
Yeah, the changes we can figure out because of the coefficients in the balanced chemical equation. Yeah. So the change for the methane, is that going to be positive or negative? It's going to be negative. We started with reactant. It's going to decrease in concentration as the products increase. So this is going to be negative. And this is where it's helpful to take this and express it as 3 times 0.004, because this will go down by 2 times 0.004. Which is 0.008. Do the math. Do not be afraid to do simple math on your calculator, because, you know, we make mistakes when we do the math in our head. At least check yourself. So this one's 0.079. Everybody with me so far? Then we need the equilibrium constant expression. And I really would encourage you to actually write this out instead of just plugging numbers in. So here we've got the concentration of C2H2 and concentration of H2 cubed. Those are the products, divided by CH4 squared. So we've got 0.004 and 0.012 cubed divided by 0.079 squared. And sometimes you can get all this set up right and then you miscommunicate with your calculator, which is a serious bummer. I'm getting 1.2 times 10 to the negative 6. Well, yeah, I'm looking back, and I realized that when I punched in .012, it gave me 2 2s. So that's why, because I'm also checking my answers against the answers in the back of the book, and that one is not quite right. So delete that one. There we go. It's 1.1 times 10 to the minus 6. You really have to show your work on these things. I mean, because we want to get the correct answer, right? If you don't want to get the correct answer, then just leave now, right? Why bother? You know, we're not that fun in here. So we all want to get the correct answer. So we need to show our work. You need to write out the ICE table. You need to write the equilibrium constant expression, plug the numbers in, use your calculator. And as I was working through these examples last night, I was checking my work against the answers in the back of the book because it is crazy easy to make a mistake. And I made several. So it happens. When you write it all out, though, you can check your work more carefully. So I punched in this number in my calculator and I got .0122. What I recommend is on a calculation like this, I did it on my calculator, do it on your calculator again. Don't just go look at what your display says. Actually punch it in again. Because a random error like that, you're probably not going to do it twice. And so then your second answer is different. Then you have to either figure out what went wrong or just go for best 2 out of 3. Any questions?